Language is weird and fascinating and weird. For instance, you certainly heard phrases like King Kong or zigzag or I don't know, click clock. And you might have noticed that if you swap the order in those pairs, so like zag or tactic, it just doesn't work anymore. It sounds funny. And would you know? And this phenomena is called a blood reduplication. So this is the phenomena that, for instance, in English, when you have those onomatopoeias such as TikTok, usually the vowels inside of them follow the I-A-O pattern, as in tic-tac-toe. And if you not follow it, it will sound funny. And you know what else is weird and fascinating and funny? Computers, I think. For the past 2 years, I've been doing some game dev. So implementing games with friends and stuff, or like GitHub's Game Off, and I became very interested in how computers work, how to write efficient code for them, especially since when you have games, they have to be like real time and whatnot. And what fascinates me the most nowadays is that in computers, we have two main types of processing objects, let's say processing compute units. We have CPUs, obviously, and GPUs. And the idea behind CPU, before that, nowadays CPUs are multi-threaded or multi-core. And what it means is that inside this single CPU, you have like sub-processors that work together to form this whole, CPU block. The core idea behind CPUs is that those blocks can do different things at the same time. So we can imagine with a pinch of salt that one of the cores is like running Firefox, the different one is like crunching some Excel numbers, and the third one is, let's say, storing stuff to your hard drive. In comparison to those 4 or 8 cores, which are typical for CPUs, in comparison, GPUs have 16,000 threads. So that's way, way more. And you'd be right to ask, what's going on in here? Why you can have GPUs with 16,000 cores, while CPUs are like 4, 8, 32, maybe if you're rich. And the core idea is that if we have some algorithm, such as this one, which does something, then on CPU, it's magic. And then on CPU, if you launched it on separate cores, all of them would be executing, let's say, different lines of this algorithm. But again, simplifying a bit, when we have GPU, the whole GPU, simplifying a bit, the whole GPU launches the same line of code with different values. So each of those 16,000 codes will have different values for the X, Y, and Z variables, but they execute the same piece of code. And at first, this might sound like a very limited, very stupid thing to do, because what would be the use case? And as it turns out, computer graphics is a very good use case, because you have all of those pixels.
Call of Duty?
Battlefield, I think, but yeah. You have all of those pixels, and you need to calculate, you need to perform some calculations to have this graphic in front of you. And for instance, one type of common calculation that you'll need to do to end up with a frame like that is related to shadows. So you will have some place in memory that tells you, for a given light, how far this light reaches into the scene. And then with this information, for each pixel on the screen, you check if this pixel is visible to this light. So you do the same operation, but for different data, for different world positions. And there are tons of stuff that GPUs do for to make this frame. We have motion blur in here, which is also a similar type of algorithm. So you need to blur some pixels to show how fast camera is moving, and you do the same algorithm but with different data. And maybe blue, which I now see is not visible that much in here, but if there's a very bright source, light source, it illuminates sort of the neighborhood to show you that it's very bright. in that area. And what I'm going to do today is that we'll be doing some live coding. Well, I'll show you how we can program GPUs in Rust. And yeah, that's basically it. I'm aiming for sort of Bob Ross vibes here, so there will be a lot of material on the way, I think, but rather than stressing you out with how much this might be, I want you to rather just sit, enjoy the show. It's like, I don't think it's like rememberable for just one watch, so just like take it easy. And before we start, my name is Patryk Wychowaniec. That's my website. I do have some Rust tutorials and whatnot, like genetic algorithms and what you would not like. You will also find contact stuff in there. And the project we'll be doing today is already on GitHub at this repository. You git clone it, you can just run it on Windows, Linux, and Macs, and it will just work.
Sorry.
Yeah, no worries. I'll also show this link later. So, yep, right. Let me mount the microphone. Three, one, yeah, back online. So let me actually show you what we will be coding today. Right. Size, I think it's all.
Stanislav Lem, Solaris.
Yeah. Yes, it's Solaris, yeah. So this is what we will be coding today. I hope the window size is all right. Do you say it? All right, maybe you can turn the lights off if it's wrong. I'm not sure. Cool. Yes, so this is our goal, and this is the place that we start with. So we have this triangle. All right, so first of all, this Rust code that I have is two modules, so to say. The first one is what actually creates this window and manages it. And this is like the boring part, which I will not show. It's like 100 lines of Rust code that you can browse it later. It's boring. And the interesting part is what's known as a shader, what you see in here. This is the code that is executed on the GPU. Now, it's a bit different from the typical Rust code, and we'll go through the differences so that it's clear. So first of all, to give a quick brief, what the difference is. This line says that since we're aiming for GPUs, and the architecture is called SPIR-V, we're aiming for GPUs, we do not have access to the standard libraries. So on GPU, we do not have file system, we cannot print stuff naturally, because it's GPU, so it's like a separate machine. Then we have a bunch of imports, which will come useful later. And now the structure, the file, is that we have two main functions. First one is called vertex shader, and vertex shader is responsible for generating triangles, because usually on GPUs all objects are triangle based. So if I were inside the game, my skin would be like 100,000 little tiny triangles forming together. And the second function here is called fragment shader. Fragment shader is responsible for generating the actual color of given part, given pixel. And like I said, usually what GPUs do, or what you would do as a game dev, is that you would generate some sort of shape from those triangles, and then color it inside the fragment shader. But what we will do today instead is that we'll generate one huge triangle so that it covers the entire screen, and then just play with the colors inside, which hopefully will be visible more later. So first of all, what do we also see here? So as the input, this function takes the vertex ID, which goes from 0, 1 to 3, 0, 1, 2, and it generates this triangle. So this piece of code determines the location of this little vertex. So if I like move it to 0, 0, it will go down. And similarly, this one is like the vertex on the right side, mine which is your left. So if I move it like that, it will go, should go to, oh, like this does the y coordinate, so this will go up and down, and this will move it to center. And the fourth coordinate is not used in here because it's just, it's used for something called perspective projection, which we do not need to worry about. And then we have the fragment shader, which generates the color. And first of all, we might see that the terminology is a bit overloaded here. So we have this vec4. It's a simple structure that contains 4 values. Those 4 values can represent like position, in which case we have like x, y, z, so 3D position. It can also represent colors, in which case we might have like green, red, green, blue, and maybe transparency, depending on the context. And the vec4 in here is like for position, while the vec4 in here is for color. So this is like red, green, blue, and this one is transparency, but we don't use transparency in here, so this would change it to yellow, I guess, and then doing this makes it white. Alright, so first things first, as I said, we won't be doing triangle magic in here. We will enlarge this triangle, which we can do by just extending the corners. Like that, not like that. Wonder what I messed up. 1, 2. Man, triangle is acting out. Right, so when I have this one, I'll just move it to... Alright, good enough. Right, so now that we have this whole triangle covered, which is probably like, extends right into here, and probably like that, but for our purposes, it's now a rectangle. We can play with the color. So first useful thing to do is that we can take the pixel position and use this pixel position to affect the color. So if this was normal rest function, we'd probably do something like that. Position, then go to vec2, which compared to vec4 contains just the x, y coordinate, and then we do some magic in here. But because we're on GPU, this is actually vec4. Where we are not interested in the last 2 places, and we need to tell to the compiler what this variable should contain. Because on its own, the compiler is not interested in the variable name. We need to add this special annotation, which in this case will be fragment coordinate. I think thanks to this, the compiler will put the x, y in this position. Right, so we have the position, and this position is in pixel coordinates, so I know for a fact that this window is 0 to 1,000, 1,500 pixels, I think. So I need to divide it, so that, for convenience, the position will go from 0 to just 1 as a float. And then hopefully this will give us some shader that actually starts to do something useful, which is this sort of nice gradient. And the convention for this is UV. So as a trivia, UV goes from 0 to 1. And what we can do now is, for instance, do some conditional logic. So let's say if we wanted to draw a circle, then by definition a circle is like a collection of points within a certain radius of the center. And we can code it directly in here. So if the UV length is less than 0.1, then we want the color. And if it's outside, we want it to be pitch black. Now we have a perfect circle, but we can also move around. This should move it to the center. UV, right, so this window is probably smaller, right, because I have different, I have smaller screen for the projector, I know it sort of looks like 750, so let's start with that and we'll see. Right, seems like yes. Right, so we have it at the center, and now what's the step in here to the third dimension? First of all, let's maybe extract this computation to a separate function. So we have circle, it takes some point, some radius, and normally we would also return, we do something like that, so also return like 0, 1 value if it's inside or outside. But as you will see in a moment, a more useful information is actually how far away are we from the circle. So if we do something like that, no, we don't check it in here, we do 0, 1. Now, instead of this Boolean information, we have that. Yeah, right. We have this information how far we are, so we know that we are inside or outside. And the route to third dimension is actually not that far from here. So in the third dimension, we have obviously a sphere, which is defined as a 3D set of points that's certain radius from the center. And now the overall algorithm that I'm going to show is called signed distance functions. And the core concept behind this is that if we have a function that tells us how far away we are from some object, and then given some camera position and camera direction to which we are looking at, we can use this information to sort of step through the world and get closer to the object. So to put it in code, if we have some function that defines the whole scene, this would be seen that consists of a sphere that's located at the 0, 0, 0, so at the center of the coordinate space, and the sphere has a radius of 1, so it's like, the scale is arbitrary, but let's say 1. And now what we need to go from the second to the third dimension is the definition of a camera. So let me try to... Alright, so a camera is defined by, 6 variables if you think about it. So we have the camera position, so if, or the eye position if you'd like. So we have the place where I have my head, and the place to which my head is like tilted towards. And you could also figure that you also kind of like rotate your head, but for our purposes, let's say it does not matter. So this also needs to have the place in the code. So we will need to have some origin. Alright. And if we have a sphere in here at the 0, 0, 0, then our origin cannot be at the same place as the sphere because we will not see it. So let's say that our origin will be at point 2, 2, 2, which is like 2 away, and then 2 away, and then 2 up. This would be very free to it can be obviously arbitrary. And then the direction is a bit more difficult one, because we might imagine that our screen is like this sheet of paper. So the sphere is here, our camera is like here, and then what we need to compute as the direction is here, is that for each of those pixels, we need to find the direction that looks at the sphere, so that we have the perspective applied. This is not terribly difficult, but it involves some matrices that I think would be awkward or long to present in here, so I just created a simple helper for that, which I will show in a moment. It was called it's command direction. It takes the origin and the pixel position to show that it is not terribly difficult. So it takes the origin of the camera, the 0 to 1 place of this sheet of paper, so to say, and returns for given pixel, so for given UV coordinate, the direction towards the center. Alright, so another missing piece of information is the actual point, 3D point, that we would hit if we were to, be this camera. The algorithm to determine that is called ray matching. It takes the origin, the direction, and returns the 3D coordinate of the object that we've hit. So naturally, we, by definition, or like the default state is that we hit nothing, which we will encode as hitting and point infinitely far away, which on its own is obviously not useful because this doesn't do anything. So now the core concept is that, maybe now microphone will be more handy. Alright. So the core concept is that we have this function, scene, which defines, given a point, the closest object from the point. So if you know this whole scene was this scene in here, then for the point in here, let's say, this function would return the distance to, I guess this would be like the closest object. If we were to execute this scene function for like a point in here, it would probably, I guess, return the distance to the down. And the useful concept about that is that what basically this function tells us is the safe step we can take at which we can check if there's an object there. So if I were in here and I was looking at this one, let's say it's 1 meter away, this function would return 1 meter. Right, I ran out of the scene. Yeah. So then I do this 1 meter step, I recheck this scene function. If it tells me that I'm very, very close, then I say good enough, this is the point that I hit. But you might have noticed that this function doesn't take the direction into account. So if I was standing in here and I wanted to check, which closest point I hit in that direction, this function still returns 1 meter before me. But I take one step in front, I still hit nothing. Then this function will tell us to check in 2 meters. Then I check 2 meters away, and I will come back. And finally, the function will at one place start returning, I guess, like this chest and stuff. And then I will be getting closer to my place in the world. So it's like conservative estimate, if you would name it like that. But it's simple because it doesn't take the right directionality into account. And it's probably simpler in code actually than explain, so let's code it quickly. Right, so the missing information here is distance, because we have origin and direction, so the only information missing is how far away from, given this direction. We will take some loop. The point we're checking is located at the origin, plus some location away from the direction. We check how close we are to anything in the world at this position. If we're close enough, then we've hit something, so let's return that. If not, then we take this step in front of us and check again later. And you might see that this is basically in some sense an infinite loop, so let's also count the number of steps we've taken. And if we've done too many, or we've went too far ahead, both arbitrarily, we just say we give up, there's probably nothing there, the function is acting out, whatever. Okay, so we have this is called ray matching, we have this written, and we can plug it in here. If match, it takes the origin and direction, and now this function returns either infinity, which means background, or some finite point. So the condition here switches to if point is finite, then we've hit something. And the sphere got larger. Isn't that exciting? No, I don't think so. So now it's time to introduce the first proper 3D concept that will make this actually look like 3D. It's called normals. So, normal is like the orientation of a given surface. So it's like a direction vector that tells us which direction the surface is facing. So if this was my hand, then the normal of it would be pointing, when one front side would be pointing upwards. And as I rotate my hand, the direction vector also changes. So then direction vector for this part would be like pointing to the left, the right, in front of me, and basically everything has almost everything has some normal vector. This is the place where our code live projector went out. So I'm pretty happy that we're still online and alive. And the question is, given this function, how do we extract the direction of the sphere at this point? Because we have a sphere, which is approximated, if we approximate pi to 1, this is a sphere, and then it has different normals all around that point to all of the directions. And this is probably like the most mathy part of this talk, because we need to actually, properly, we need to take the derivative of this function, but we cannot, for this view we could, but in general we cannot. And I have some extra slides to show what I mean. Okay, 1 minute, when add on derivatives. If somebody doesn't know, when we have a function, we can take its derivative, which is, if we're given a point, the derivative is like this tangent, well, let's say line to the point. And we can take derivatives, obviously, analytically. So if we have some function, we can sometimes compute the precise derivative. But in general, if we had, let's say cube, whatever, some random shapes in the scene, we would not be able to derive this analytically. So what we can do instead is that we look at the neighborhood of our point, very small neighborhood, so like minus 0,0,0,1 plus 0,0,0,1. And if we take their difference, this sort of approximates, very close difference, this sort of approximates this tangent line. And approximation is good enough because computer graphics is mostly smoke and mirrors, so. Alright, so what we need to write is that this normal function takes world position, it returns some direction vector. As I said, we need to take small steps around the point we're given, so something like this should do it. And we have 3 dimensions to check, so we have to check the x coordinate, the y coordinate, and z coordinate. Oops. D. So there's like a small step around those 3 axes. And now what this g stands is like a gradient, so the gradient is like this difference between those 2 points is that we look at the scene at point plus, point minus. We do this for all points in here, so alright, so this just approximates this, derivation. For our purposes, what it returns us is, as you'll see, this sort of rotation at given point. And it needs, let me just quickly reiterate how neat it is that we have 3D coordinates that use x, y, z, and the colors also are like 3D points already we don't use, so this means that we can just visualize this 3D direction with just basically colors. And voila! It sort of starts to look like 3D. We can try to move the camera. So this coordinate was the height, so like the y coordinate up and down. if we move it to 0, 0, we're moving down. Then -2 is like from the bottom, and then we can move far away, far away. Alright, so rotation is neat, but what we can do with this? We can do lighting. Yes, I always mix lighting and lightning, so no, lighting. And for that, we just need one simple concept. It's called dot product. But for our practical purposes, what dot product is like given two directions. Dot product is similarity factor of them. So if we have two directions like that, dot product of them is 1. Then as they start to diverge, the dot product goes to 0, and then becomes negative. And this exactly corresponds to how lighting works. So if we have a flat surface, then as I move, let's say that this is the surface, this is the light source. If the light source is perfectly on top of the surface, it gets 100% of the light. Then as the light is like getting down, down, and down, and this angle between them changes, the surface becomes darker and darker. So let's say that we have this similarity factor. And that let's say that our light is just, the sky, so it's on the top of us. And so now, instead of this, we can try to do, back 4. So this would be the white color, pure white color. If we multiply it by the similarity factor, we start to get some shading. And let me quickly change that to actual nice color. I think crimson, it went like that. Yeah, okay. Now, as we as we move the light, but for that we need one more thing. For more math-oriented people, the similarity factor is actually the cosine of the angle, so we can name it like that, because if cosine of 0 is 1, then cosine of, I guess, like pi is 0, and then it goes negative. Decant, similarity factor. And one key point we need before moving forward is that currently, for each point, we check if the light is, above it. So if we would imagine very, long surface and light, like a point light in here, then for each point on the sphere, it's not like the light is, above all of the points. It's like in one point, so the angle is different. So this, cosine should be different for each point. So what we actually need to do is take a look, place the light somewhere in this scene. So let's say it's, like that. And then we have to compute this angle between the surface we've hit and the point. Minus point. And this will come a bit important later. And one more cool lighting thing we can do is that we have this one type of lighting which is called diffuse lighting. It's like the base color of an object, so to say. But this is not the only kind of lighting that we could have. So we have this diffuse lighting, which is this one, times the cosine. But there's also a thing called specular highlight. So if you imagine like a metal object, and then if you have a light that shines at the right angle, you see like the light reflecting more, at certain angles of this metal surface. This is called specular highlight, and you can approximate it in here, because it looks very, very nice. So instead of taking just the cosine, we'll take it to some power. And how this looks like is that we add both of them. We add the W coordinate, which we don't use anyway, but need to satisfy. And voila, this is, nice, simple touch, but it adds much more to the readability of the scene. Now this is, I think spheres I need, obviously. Hexagons are better, but I know we can fight on that. But one cool thing you can do with this sine distance function is that you can basically play with them to see what comes out of this equation, because now everyone knows how a sphere looks like. I hope you've all seen some boxes in your life, or maybe triangles. But like, what would happen if we would, instead of hard coding, just radius to 1, what would happen if we would like do some multiplication that is basically, I don't know, hard to imagine, so what this...
Maybe cosinus.
I have an example of sine, which we can then check if it works with cosine, because now it makes me curious. But let's start with sine. So I do not really have an intuitive explanation for what this does. So like for spheres is easy to understand. This one is just like something you might randomly stumble upon, and this is part of what I would like to show. You have this algorithm that you can essentially play with and see what comes out of it. And for this, we need to actually move the camera a bit further, like that. We can make the sphere a bit bigger, and let's do some, it's basically random stuff that you can do. Let's say that I do this. And yes, total, no, this should be minus, yeah. All right, and we need to move the light a bit, so let's move the light at our position as well. All right, so we have triangle-ish with like dent inside of it. And what we can do is that first, if we extract this,
it's a bike saddle.
It's what?
Bike saddle.
It's bike seat, right?
Yeah.
Yeah. What we can do is we can sort of animate it. So we might notice that if we multiply those by, some, what's the word I'm looking for? Disfiguration factor, let's call it. Then disfiguration of 0.0, which will bring us the sphere again. So let me save it. Disfiguration of 1 will make this bike seat. And what we can do to animate it is that we can pass the time from the application and change this disfiguration factor with time. And I think the output will be very nice, but we need to first pass the time in here. So let's assume that we have time. Or maybe no, let's start from the top. So we have this input, so the main function of our shader. It takes the position which we already added at the start, and now how we can pass time. And this looks sort of more magic because you cannot just pass values from the application Rust that calls this function. It doesn't call it directly. You sort of instruct the GPU driver to do it. So passing stuff requires some trickery. Basically, you have to have a struct, which I've already declared in different functions. Since this is actual, then we provide the width and height, which I've hard-coded to 715 there. It also passes the time. And this is what you would do if this was normal code, but because this is GPU driver, we need to pass some extra metadata so that the compiler and GPU knows what they are doing. It's called descriptor set and binding, the type of the binding. And what this means basically is that this is sort of like the index, because if you have multiple params, you can index them with this descriptor sets and bindings, and you just sort of map it on the application side. In this case, it's just like the first and the first. And then this is the type of the binding, which there's like different one for arrays and different one for structs, but for our purpose, it's just like simple struct. The struct has time in it. And yes, we need this to pass this time up to this scene. So this requires a few modifications because, first of all, we call this scene in the ray matcher. Right, so we have time. And also the normal function also now depends on the time because it also invokes this scene function. So like that. And oh yeah, that's true. It's this one. All right. The code compiles. So now what we can do, we could pass the time directly, but since we know that this factor, or well, I know that this factor only works in cases between -1 and 1, and the time already went to like 30 minutes on this type factor, then what we can do is just take the sign of it, so that it's like this wave. Now, it deforms badly, in my opinion, for the negative values, so let's take the absolute value. Now we can speed it up a bit. Now if we do one final touch and square it, we'll have this sort of kick to it. And I know this is not terribly difficult, it feels random, and like I said, there is no, I have not managed to prepare an intuition, but what I like about it is that you can basically play with it to see what comes out of it. We can see what does cosine doing here, but I think this will be the same animation. Yeah, sort of changed. We can do, like tangent, whatever.
Oh, that's nice.
Yeah. And for comparison, if you would like to do that with typical graphics and do like GPU with triangles and stuff, this would be terribly difficult. But in this, it's like, whoops, this like defines our whole scene. And yep. So what comes next is that we will do this ocean animation. And yep, wondering if I have not missed anything, but I think not. So I will introduce one more concept related to signed distance function, which is how to, sort of join them together. Because you might think that having one sphere is nice, but I'm rich, I would like to have 2 spheres. Or you're very rich, you want to have 4 spheres. Oh my god! And it's actually easy. So just to quickly do, if we have one sphere in here, which will move around a bit, so like, to the side, and needs to be smaller probably. Then we have second sphere, which will be mirrored. Then if we pass the distance to the first, we'll get the first, distance to the second, we'll get the second. And intuitively you might think that we should pass maybe the sum of the distances, but then it doesn't work. And what we actually need to do is that take the minimum distance out of them, because as we cited, this scene function should always return the minimum distance to the closest object. And then the frame matching algorithm, it will find this hit point, but it needs to, for the scene to be reasonably behaved. So if we take the minimum, it will actually find both spheres. And for the ocean, we'll actually do something a bit different. So let's first start with the ocean. It's also signed distance function. Let's start with just our flat plane. Yeah, I'll leave the sphere in here. So this will print just a flat plane. That's because this will sort of nudge the rail matching algorithm to find the surface below it. If we change this to x, we have a wall. If I only don't make the mistake in here, this gets us out of the wall. And now if you... No, wait, let's start with the color. I almost forgot about the color. This should be blue, which should be something like that, I guess. Good enough? Yes, so we have the ocean, and the object we had at the beginning was like oceany sphere. So we have sphere in here, make it bigger. We have ocean in here, and we know that if we take the minimum, it creates this sort of, it joins 2 shapes together. And in here it failed to find the solution. The plane is there, but we probably hit this 64 steps limit, so this is just a quirk. It will disappear in a moment. So minimum finds the union of 2 shapes, and to find the common area we should do maximum, which returns the common area between what I've mistakenly named plane. This is actually like a box that spans from the 0 up to infinity below. Because if this was just a plane, then this part, wouldn't be visible, but it's a box. we make it a bit bigger, maybe like that. Alright, and we can affect, the height of each pixel or each word place by modifying the distance returned in here. So, like that. The general form is like this. So, h, which stands for height. If height is 0, we have basic. Height 1 brings it to the top. Height negative to the bottom. And we've made, a lot of signs in here. So, and the sign looks sort of like an ocean. So, if we again take the sine wave, we will get sort of the ocean's vibes, the second sine wave to get the 2D ocean. And yes, I will be coming to an end, but not with the simulation yet. What I wanted to say is that now I'm sort of stopping to explain. This is the last part when I will just write this about 20-line algorithm. And I'm mentioning it because how to phrase it? I can phrase it. I can put it in directly. I was not able to find accurate explanation that would fit in 10 minutes. So I wanted to just sort of chill out if you have not, see how the code plays out. It's not terribly difficult, and as I said, the repository with more comments is also at my GitHub, which I'll show later. And yes, let's do some ocean coding. Oh, I can do some high-level explanation of what's going on. This is like one level of sine waves, and what the code will do is that we will take 16 different sine waves, randomly shifted, and sort of join them together. And as you will later see, it actually creates a nice oceany like simulation. All right.
Maybe we can play some music.
Skibidi toilet, yeah. I'm not sure. I could have prepared the music, yeah. So we have frequency.
We're playing what H_3 mutable does.
Yes, so this, well, if there are questions, I can actually try to explain. So this will be a weighted sum. So this will be like sum of the values and then sum of the weights. And this is just like a weighted sum of the waves. This just generates some noise, and sine and cosine happens to align with what we need. Then, yep. Right, 3 more to go. So we need to multiply the frequency.
And I wonder where we change the value of noise, because it seems at the beginning, okay, got it.
Okay, yes. Now let's try it. See if it doesn't blow up in my face. Oh, maybe I've made a mistake. Maybe I have not saved. Okay. There's a variable with the same name, t. Right, I have not passed time in here, right. And it's animation, so I should have time. Voila! We have ocean. There are a few more things we can add to the simulation, like, we can make it faster if we multiply the time, so like...
Can we make it greasy brownish, just like Odre River?
If you know some RGB color for brown, we can. I know for green because 0010.
Okay.
No, this is more blue, which is not correct. Yes, this is my spawn. Yeah. Alright, we can also move the light a bit further to see that this highlight is still there. And yes, I guess thank you. Just before we finish, I do have one more topic to like due diligence to say. So one of the questions I'm getting on Code Live is that whether you can use Rust to write like shaders that operate on data, not only on graphics, which is you can use computer shaders as is known. And also I should say that if you're like learning Rust, then probably starting with shaders is not the greatest thing you can do, because this is not like what I'm showing here looks like typical Rust, but like there are some quirks, especially with graphics, that can be difficult to wrap one's mind around if you are both learning Rust and graphics at the same time. I would encourage you to play with it. I'll show the repository once again if you'd like to check it out. Like I said, it should work on basically every system, maybe except FreeBSD. Sorry for that. Yeah. Thank you. Oh, I guess also, do we have questions? Because I think this would be important. Yeah.
Yes, there are
questions. I want to ask first myself, because then I will lose the microphone. Why this is so weakly typed? I mean, you only have like vec4, vec3, and this only the only type information here is the length of this vector. Wouldn't it be better to have like dedicated color and space types or whatever?
Yes, and there are libraries which allow you to do that. I forgot the name, but I was reading about one even recently, so maybe posted on the Rust GPU project somewhere. There are, but it's like still sort of bare bones. So another due diligence part I should mention is that this does not use LLVM, so this is Rust, but it doesn't go from LLVM, so it doesn't have all of the optimizations typical Rust code would have. Instead, it's like train lift. It's not crane lift, it's like crane lift, so it's like dedicated backend to generating code. So it doesn't do all of the optimizations. And for instance, it optimizes for loops and while loops differently, and while loops are faster than for loops, so it has some quirks like that. It has sometimes miscompilations, so you end up with wrong shader. You've written something correctly, but it doesn't work, not because you did something wrong, but because the compiler is like sorting itself out. So there are still some rough edges. And one of those rough edges is, I guess, like this weak typing, as you mentioned.
Right, so I'm interested in what rendering API you use, because you only showed the GPU part of shaders, but you didn't show any of the backend.
Yeah. I was actually thinking whether to show the backend side. It's WGPU, so it uses bare bones. I'll close this one because it hogs the GPU and cannot scroll. Uses Winit and WGPU, so this is just basic window initialization. No, scrolling doesn't work, so I'll have to refer to this. I'm using the pixels crate as well because it facilitates some of the stuff. And the rendering part, alright, should be in here. So in here we might see that I'm initializing the GPU module. I pass the compiled shader in here. Then I initialize the texture for the output that we've seen. Move to top, yeah. And then it's just creating buffers and stuff, but it's like WGPU, and that's why it should work on all three major systems, because WGPU like unionizes is the better word, like unifies them all.
Okay, cool.
Any more questions?
Okay, I can ask some question, but I'm not sure about this applicability of this question. Do you run it on internal GPU, or do you manage to run it on dedicated graphic card?
Yes, so in this case, I have a Mac which has...
It's enough that you have Mac.
Yes, I mentioned I have Mac. Thank you. Next question. No, it works on dedicated GPUs as well. It has even an env option called WGPU power pref, like power preference, which allows you to switch between one or the other. Or even if you have multiple GPUs, pick whichever one you want. I've tested it, on my Mac and both on, I think, Vega, AMD Vega back at home. So it works, I think, everywhere because it uses this unified standard. So
OpenGL.
so actually, what this does is to quickly describe the history. Like we have Windows. On Windows, we have DirectX, which provides graphical facilities. On Apple, you have Metal, which is like its own set of API interfaces. It's not common with DirectX. And on Linux and sort of Windows as well, you have Vulkan. And what this WGPU create does is that it provides you this unified interface like create buffer, which internally translates into whatever this particular window, this particular OS needs to actually create a buffer. And because those APIs are like the same for dedicated and built-in parts, GPUs, so it works everywhere.
Mm-hmm. So it's using some wrapper around OS native graphical.
Yes. So if you were to like go into definition to what happens internally, you would eventually find some code that checks if I'm running on Windows, do this. If it is Linux, do that.
All right. Niti, thank you.
Yeah, one more thing regarding the backends you mentioned.
Mm-hmm.
Have you tried to write graphics in some raw bindings for the platform-specific API? Instead of platform agnostic with GPU?
Mm-hmm. I have not. To be fair, I'm a little. For Mac especially, I have not played with its API like at all, and there are some bugs that I would like to fix. For instance, in WGPU, or maybe like, for instance, on macOS, one thing that it's problematic for me is that when you bind textures to your shader, you can only bind like 16 of them because of internal limits. And this works correctly on Windows and Linux, but on Mac it's got this 16 textures limit, and there is issue to solve this. It requires writing some, Apple specific code that I would really like to write, but I'm pretty scared because it touches this Object-C or whatever they have.
Thanks.
So yeah. So now I have only used WGPU, but it's pretty powerful. As far as I went, it has everything I've ever needed. So
Okay, cool. Thanks.
Any more questions? So huge shout outs to Patryk.